I'm going to work through an example of motion in 2 dimensions. This is a nice example because on the one hand it's going to remind us of a lot of mathematics that we may not use like each and every day, but it's a good thing to have in our mind as we do this class. And the other thing is it introduces the idea of a collision, which in physics, collision just means I have two things at the same place at the same time. So in terms of like trajectories, collision means that the positions of two objects are the same, so you can set them up as an equality at the same time. So our setup is some motion in the xy plane. Object A is going to move just to the right, and it has a constant velocity, no acceleration. So the velocity vector for this puck A is 3 meters per second, and it is entirely along what we're taking to be the x direction. The acceleration of object B is fixed at a value of 0.4 meters per second squared, and that's constant. So this is an example of motion with a constant acceleration. And then the thing that we actually want to find is what is this angle theta that the trajectory of puck B makes with the y-axis. So we're solving for an unknown angle. So that's a little different. As you'll see, that gives us a set of equations that are a little different compared to what we normally have for just good old-fashioned vanilla kinematics. So let's go through some things that we know. So for puck A, its final position is its constant speed times the final time, and its y position is a constant 30 meters because the origin is there, and this is 30 meters. Okay. For the puck B, what do we know? That's a little more complicated because it's a constant acceleration, and we have to describe its trajectory in terms of x and y components. So for B, we'll start off with the equations for the components of its velocity. The x component of its final velocity is going to be the x component of its initial velocity plus a sine theta times time. And this started off at no initial velocity, so I can throw that term out. And we have a similar equation for the y component of puck B's final velocity. B initial y component plus a cosine theta t. And again, no initial velocity on the y direction for puck B, so that goes to 0. Now, let's make sure that these trig functions are making sense for us. This acceleration vector is constant, and it is the opposite side that's going to align with the x-axis, and it's the adjacent side that aligns with the y-axis. And that might be giving you a little pause because I have an x with a sine and a y with a cosine. It's perfectly fine. We're measuring the angle from the y-axis, not from the x-axis. So another one of the reasons why it's important to have a diagram, and you know what it is you're doing. Okay, so those are the velocity components for puck B. Where is it? So then we write out expressions for, it would be the displacement, but it's starting at the origin. So I'm just subtracting off of 0. So just go ahead and suppress that here in just a second. So we have the initial x position plus, for completeness, the x component of the initial velocity times time plus a half a sine theta, the component of the acceleration along the x direction, and then time squared. And we have a similar looking equation for the y component. The b0 y component times time plus a half a cosine theta times squared. And I can throw away a bunch of terms because we're measuring relative to the origin, and puck B has no initial velocity. All right, and then one of our pieces of insight from working out this problem is concluding what a collision means. Collision means being in the same place at the same time. So let's apply that idea. At some time, if they're going to collide, the x coordinates of the two pucks are identical. So we have an equation, and that tells us that the constant velocity of puck A times time is going to equal a half a sine theta time squared. And I can throw away 1 power of t. And then the other equation that we can use to figure out when and where the collision is that the y coordinates of puck A and B have to agree with each other for some particular time. And then this is just a constant, y sub A, and that has to equal a half acceleration cosine theta times squared. Okay. We're going to use this equation to solve for time, the final time. And this is a sufficiently long problem. I'm going to jump ahead to another page. So what we've learned is that the final time is equal to twice A's velocity over the acceleration sine theta. And we know some of these things. So this is going to be 2VA is 6 meters per second over, the acceleration was 0.4 meter per second squared, and then I have sine of theta, which remains unknown because we don't know theta yet. That's the thing we're trying to solve for. What's the angle at which those two are in the same place at the same time? So that works out to be 15 seconds over sine of theta, if you just want to scroll that away. All right, so we have a form for time. Let's eliminate time in the second equation that we had for the condition that there's a collision. And so that was to say that the y-coordinate of puck A at the collision would have to equal a half acceleration cosine theta, and then there's a time squared, but we have a new expression for what the time of collision has to be, and we can pop that in instead. And it is twice velocity of A over the acceleration sine theta, and then it was quadratic in time, so that's squared. And cleaning that up a little bit, we get 2 speed of A squared over the acceleration, and that's cos theta over sine squared theta. And then if we put in numerical values, the y-coordinate of puck A is fixed at 30 meters. This combination of twice the velocity of puck A squared divided by the acceleration works out to be 45 meters. And I have a cosine theta over a sine squared theta, which you might remember I can get a tangent out of that, but I still have 2 trig functions. So this isn't as simple as doing arc cosine. It's going to clean this up for me. I can simplify it a little bit. I could divide both sides by 30 meters, and this is going to give me 1 is equal to 3/2 cosine theta over sine squared theta. So now what do we do? Well, a handy identity from trigonometry is that 1, I have to be able to rewrite that as cosine squared theta plus sine squared theta for any value of theta. So this sine squared theta, that has to equal 1 minus cos squared theta. That looks like it might be helpful, because then I'll have a cosine theta, a no cosine theta, and a cosine squared theta, which is suggesting a substitution. 1 is equal to 3/2 cosine theta over 1 minus cos squared theta. And I can rewrite that as 1 minus cosine squared theta will equal 3/2 cosine theta. Get everything on one side, move over the cosine squared theta, move over the 1, and we have what is suggestive of a quadratic equation, as it should be, in cosine theta. So let x be cosine theta. So this will be in a form maybe you're a little bit more comfortable with. X squared plus 3/2 x minus 1 must equal 0 at the collision. Okay. And this is our old friend, the quadratic equation, where we have a equal to 1, we have b of 3/2, and then c C is minus 1. So we'll collect those terms. A equals 1. B equals plus 3/2. C is equal to minus 1. And the suggestive choice of variables is because we remember the solution of the quadratic equation. The roots of this quadratic equation, or a quadratic equation in general, are x equals minus b plus or minus, because there are two roots, b squared minus 4ac, all under a radical, and then in the denominator, 2a. So we have our values of a, b, and c. We just plug those in. So I have a minus 3/2 plus minus, and under the radical we'll have a 9/4 plus 4, and then a 2a, which is just 2. All right, I'm going to move to the next page. And we'll finish up our two possible roots. So we are at x is equal to, divide everything by 2. I'm going to have a minus 3/4 plus minus a half. And then under the radical is 9/4 plus 4 is 16/4, all square root. So that's minus 3/4 plus minus a half, and then root of 25/4. Okay. And that is going to give us solutions x equal to minus 3/4 plus minus a half of 5/2, which is plus minus 5/4. So this is, if we take the minus root, minus 3/4 minus 5/4 is minus 8/4, also known as minus 2. Or we could have minus 3/4 plus 5/4 is going to give us plus a half. All right, so why are there two roots? What do these mean? Which one do we want? Well, there are two roots. Going back to our picture, there is an arrangement where this could happen where this is the instant t equals 0. There is an arrangement that happens 1/2 second into the future where a and b will meet. But there also was another time in the past where we could have done this before puck A crossed x equals 0. So there was a time in the past where we could have launched B, puck B, and had A and B collide. Okay, so there are two possible solutions, but we want the one that is in the future. So we want this guy, x equal to 1/2. Okay, so we reminded you of the quadratic equation. The next thing I want to remind you of are our favorite little triangles from trigonometry. So far we know x is equal to cosine theta, and we know x is equal to 1/2. But what is theta equal to? Well, I've done this a while, so I will just go ahead and write down that that is true. For theta, the arc cosine of 1/2 must be 60 degrees. Now, how do I remember that? Well, I remember a couple right triangles that someone taught me once upon a time. We got that one, and then we've got equilateral triangle. And we can fill in angles. This one is our 45, 45, 90. The other one that is good to keep present in your mind is the 30, 60, 90 right triangle. And that right triangle, this side is 2, that side is 1, that side is √3. And then for the 45, 45, 90 right triangle, opposite and adjacent are 1, and the hypotenuse is √2. So a half, right, is for cosine theta adjacent over hypotenuse. So we're looking at the 60 degrees. So that's how I knew that this should be 60 degrees. All right. So let's check our answer. When does this collision happen? It happens at a time, we got the where. Now let's do the when. 2 times the speed of puck A over the acceleration and sine of theta. And we had found before that was 15 seconds over sine of theta, and sine of 60 degrees is going to give me √3 over 2. So I put in a √3 over 2, the 2 flips up, and we'll have the time of the collision in the future is 30 over √3 seconds. Okay. So we know our when. Let's just double check that this answer doesn't have algebra errors in it, because everyone is prone to making algebra errors. So let's ask, are those x coordinates really agreeing for that time? By construction, they should be, but let's double check just to be careful. So I have half the acceleration of puck B, I have a sine of theta, and then it is quadratic in time squared. So that's telling us, since we have the time, 3 meters per second times 30 over √3 seconds. Is that equal to half of 0.4 meters per second squared? We have a sine of theta, so sine of 60 is our new best friend, √3 over 2. And then time squared is 30 seconds over √3 quantity squared. All right, so on the left-hand side, I have 90 over √3 meters. And what do I have on the right-hand side? It's a half of 0.4, which is 0.2. So I'll have a 2 over 10. I'll have a meter. The second squared will cancel out with that second squared. So at least dimensionally, things are okay. So I have 2/10 of a meter. What else do I know? I have a √3 over 2. I have a 30 squared, which is 900. And I have a √3 squared, which is 3. Okay, so this is going to simplify a bit. I can get rid of a 2 and a 2. And dividing by 10 is the easiest thing in the world, since we are base 10 in our counting. So left-hand side, 90 over √3 meters. And right-hand side is looking pretty good. I have a 90 √3 over 3. So it's also a 90 over √3 meters. Okay. Chink. All right. So we know the collision happens at a time of 30 over √3 seconds. It happens, let's go back into my notes. It must be at the y coordinate of 30 meters, and it happens at an x coordinate of 90 over √3 meters. And that is the collision that happens in the future, because we have t equal to 0 when the x coordinates of the two pucks are both 0. So we have a when and we have a where, which is exactly what we're asked to solve for. So there we go.